Hi everybody, welcome back to another video on Feynman integration. Today we're going to be evaluating the Gaussian integral again, but this time we're going to be using the general form of the Leibniz integral rule, and that is written right there. I'm not going to prove that. If you'd like a good, solid explanation of why that's true, head on over to the channel Flammable Maths, and he's got a really good demonstration of why that's true. I will post a link to that video in the description. And also, I want to just say that this is where we get the special case of the Leibniz integral rule, which is what we've been using up to this point. You can see that in the general form, the bounds of integration are functions of t. And if you differentiate with respect to t, a constant, you get 0. So with constant bounds of integration where a of t and b of t are constant, this part will drop out, because if you take the derivative with respect to t of a constant, you get 0, leaving you nothing but the integral from a constant to another constant of the partial with respect to t of f of x of t, which is what we've been using up to this point. But today we're going to be using that one right there. I'm going to skip a lot of the busy work in this video. All the stuff I skip is stuff that anybody with knowledge of Calc 1 and 2 would be able to do on their own. So I'm not going to really spend a lot of time on that. So anyway, our first step in evaluating the Gaussian integral using the Leibniz rule is to create a function of t that is equal to this right here. Our next step is to differentiate both sides of that with respect to t. And if you use the power rule and the chain rule and the Leibniz rule over there, you'll get that f prime of t is equal to 2 times the integral from 0 to t of e to the negative x squared dx times e to the negative t squared. Real quick, the reason why I inserted that times 1 right there is to just help you visualize that this can be considered a function of x and t, with our t simply being 1. And I did that to help you plug it into that formula over there. Go ahead, pause the video, and wrap your head around why this is true. Plug the values in to that formula, use the power rule, use the chain rule, and you will find that f prime of t is indeed equal to this. I highly recommend you do that because we're going to be using the Leibniz rule, the general form of it, a lot in upcoming videos. So getting some practice on it would be good. I really want you to know why this is true. So anyway, we have f prime of t. I rewrote it a little bit different down here, and then made a substitution where x is equal to t times some new variable u, giving us dx is equal to t du. Applying that substitution gives you this. I'm not going to go through why that's true. First and second semester calculus will take care of that. The next step is kind of a little bit of fancy pants math, as Professor Leonard would call it. I just rewrote this integrand right here as the partial with respect to t of some other function. That's written right there. You can see that if you take the derivative with respect to t of this thing, you'll get this thing. So it's just another way of writing f prime of t. The reason I did that was because if you remember with the special case of the Leibniz rule, what that allows you to do is bring a derivative inside the integral sign. If it allows you to bring it in, it'll allow you to bring it out. So this could be f prime of t is equal to the derivative with respect to t of the integral from 0 to 1 of this junk right here. And as you know, if you take the indefinite integral with respect to t of a function that has been differentiated with respect to t, you get back the original function, and that is demonstrated in this next step right here. Pause the video and verify that for yourself. Of course, the plus c is important. So now we have two expressions for f of t. We have f of t is equal to this chunk, and we have f of t is equal to this chunk, and that is stated in this step right here. F of t is equal to some junk, which is also equal to some other junk. Now, letting t approach 0 will give the following. It will give us f of 0 is equal to, well, I hope you can see that if we let t approach 0, this part will be 0. So we have f of 0 is equal to 0, which is in turn equal to the integral from 0 to 1 of this whole thing becomes 1, or negative 1, I'm sorry. So we have it's equal to the integral from 0 to 1 of negative 1 over u squared plus 1 du. And that's a pretty common integral that that'll be negative pi over 4. So again, taking t is equal to 0, we get that 0 is equal to negative pi over 4 plus c, giving us that c is equal to pi over 4. And I'm just going to go ahead and write that in right now. We know that c is pi over 4, so we'll just put it there. So let's remember what our original goal was. Our original goal was to evaluate this. Well, you can see we almost have that right here. We just need to let t be infinity. So let's evaluate f at infinity. If we do that, we get that the integral from 0 to infinity of e to the negative x squared dx all squared is equal to, well, it's equal to this part where t is equal to infinity. And if you let t approach infinity, this whole thing will evaluate to 0. So basically what we get is that this thing squared, which is I squared, is equal to pi over 4, stated right there. And the next step is pretty simple. You just take the square root on both sides, giving you I is equal to pi over 4. And that's it. The Gaussian integral evaluated yet again. I hope you enjoyed that.